Now we're going to talk about exponential growth and exponential decay. So everyone has had a great example, unfortunately, of exponential growth, which has been the coronavirus, right? It has grown exponentially like that. We learned more about exponential growth than you ever wanted to know. But the thing about the exponential growth is you can always look at that base, the growth factor. How fast is it growing? And this was data that was really used to make decisions, right? The growth factor is always the base. So like here is 2, or here it's 2. It doesn't include the 3, or here it's 4, or here it's 4. But I feel like I want to always change one. I think there's one where it's like y equals 1/2 to the x. Wait, no, not 1/2 to the x. Okay, never mind. Sorry, I'm thinking of decay. Yeah, so that's that. So our exponential growth models use this formula, which I don't think you have to memorize. No, you do not have to memorize that. Y is the final amount, A is the initial amount, R is the rate, and T is the time. So here it's talking about buffalo. Like buffalo grew at 7% a year. Can we write a model for this? So yeah, sure. So Y equals the initial amount, which is 38 times 1 plus 0.07 to the t. So that's our function. Or you could say y equals 38 times 1.07 to the t. Then they want us to evaluate that after 7 years. So really this is a function. I mean, I could even write it in function form. And it wants me to evaluate f of 7. Or what happens after 7 years. So 38 times 1.07 to the 7th power. So I would just take my calculator and type in 38 times 1.07 to the 7th power. I'm going to have to round that to approximately 61 buffalo. Sorry. So now for the graph, you're going to want to type this in your calculator like y equals 38 times 1.07 to the 7th. Or sorry, 1.07 to the t power, right, or x, whatever. That's going to be hard to represent here on this graph, right? So if we represent it here, raised to the x power, y equals 38 1.07 raised to the x power, and graph it, right? You should see the thing shooting up. Now you're going to have to adjust your window, right? Because your normal window just goes from 10 to negative 10. We really only care about the first quadrant. So this is hard to explain without showing it on the calculator, but you're going to go to your window. I would make your x min like -1, and your x is years, so maybe you can go up to like 10 years. And then I would make the y min -10, and maybe it goes up to like 150 buffalo, let's say. And then graph it. And then you'll be able to see the graph of the buffalo getting bigger and bigger. Here's the thing. You can't type in y equals 80. That's what that is. That's asking for the buffalo. So that's the y. So you have to use your trace key and then just kind of march your trace key up and down until you see the y value get to 80, or as close as you can. Right? So I'm marching mine here. It looks like I'm at 74, 75. And then getting close to 80 at about 11.05 years. So I'll just call it 11 years. And we'll show that in class more clearly how to estimate it using the graph. Here's another version of the exponential growth equation. This is with compounding, where n is equal to the number of times that the interest is compounded every year. So let's see, the final amount A, or I should say A, is equal to the principal, which is 2,900, 1 plus 0.035 over, annually means it's compounded once a year, and then find the balance after 3 years, 1 times 3. So what I'm going to type in my calculator is 2,900 times 1.035 cubed. And I can just do this on the regular screen, 2,900 times 1.035 cubed, and I'm going to round it to the nearest penny. So 3215.28. So pretty good, right? From investing $2,900 for 3 years. What would happen if that money is invested quarterly? So this is 1 plus 0.035 over 4 to the 4 times 3. So that's like a tall glass of water there. So I'm just going to type that in my calculator as is, 1 plus 0.035 divided by 4, and then raise that whole thing to the 12th power. And here I see I get a little bit more money, 3219.59. So compounding quarterly gave me more money than compounding annually. Do you think it's going to give me more money or less money to compound monthly? Monthly is 12 times a year. Let's see. 2,900 times 1 plus 0.035 divided by n, which is 12, and then raised to the n times t. And so this turns out to be 3,220.57. So definitely getting the most money with the compounding monthly. So this is exponential growth.